Okay, students. Now we'll see the error detection and correction techniques. Okay. Now this is n comma k. This is the representation of a block code. Which code? This is the representation of block code where n is code length. Code means that ones and zeros. Okay, information. This is code length. This k is message bit length or information message bits or information bits length, or sometimes called as data bits length. All are same. Okay, clear or not? So this is a block code representation where n is code length, k is message bit length or information bit length or data bit length, where n minus k, which is nothing but m, where m is number of parity bits. So finally, ultimately, the n, which is equal to k plus m. So a code consisting of what? A code consisting of data bits length, which means information bit length, as well as parity bits. Okay, this is the final conclusion. Okay, so a code, the code information, the code consisting of data bit length means data bits as well as parity bits. Okay, so the code is nothing but information bits plus parity bits. Okay, data bits plus parity bits. Okay. This is a representation of block code where n is code, k is data bit length. Okay, so in such a situation, now I want to find how many errors are detected and how many errors are corrected. Okay, so a code is capable of detecting small t1 errors. A code is capable of detecting small t1 errors if the following condition is satisfied. The following condition is nothing but d minimum is greater than or equal to t1 plus 1. So a code is capable of detecting t1 errors if this condition is satisfied, which means a d minimum here is nothing but this is a d minimum. This is minimum Hamming distance. Okay, how to find that we will see. Okay, minimum Hamming distance. This is the minimum, d minimum. So if it is if the minimum Hamming distance is here, if minimum Hamming distance is 3, means if minimum Hamming distance is 3, so then 2 errors are detecting. Now see here, this is 3, which is greater than or equal to 2 plus 1. So T1, which is equal to 2. 2 errors are, if minimum Hamming distance is 3, now 2 errors are detected. Okay, so if detecting 2 errors, then the minimum Hamming distance is 3. Clear or not? Note on this. Detecting 2 errors. This is the condition for detecting T1 errors. Now, for correcting T2 errors, this is for detection. For correcting T2 errors, the following condition is satisfied. So, the minimum, which is greater than or equal to 2 into T2 plus 1 for correcting T2 errors. Now, the following conditions should be satisfied. For example, if minimum Hamming distance is 5, so now T2 which is equal to 2, which is equal to 2. Now correcting two errors. Okay. If minimum Hamming distance is 5, correcting 2 errors, and T1 is how much? 4 plus 1. Now detecting 4 errors. If minimum Hamming distance is 5. Okay. Now this is a detection and correction. How many errors are detected or corrected, and depends upon the Hamming distance, minimum Hamming distance. Okay. Now this is this we can identify when a Hamming distance is known to you, right? Now in a n comma k block code, this is in a n comma k block code capable of correcting T errors. Correction. For correcting T errors, then this condition should be satisfied. 2 power n minus k, which is greater than or equal to summation I equal to 0 to t nci. The code is capable of correcting T errors, then the following conditions should be satisfied. 2 power n minus k greater than or equal to 2 power n minus k, which is greater than or equal to summation I equal to 0 to t nci. So if it is correcting only one error, means t equal to 1, 2 power n minus k, which is greater than or equal to summation I equal to 0 to 1 nci, which is equal to 2 power n minus k, which is greater than or equal to nc0 plus nc1. So 2 power n minus k, which is greater than or equal to, this is 1 and this is n plus 1. Now this is for correcting single error, am I not? For correcting single error. Now for correcting T errors, then for correcting one error, this is the condition. Now in this equality condition, equality condition is nothing but 2 power n minus k, which is exactly equal to n plus 1. Now, if single error correction equality condition is satisfied, if this condition is satisfied, that n comma k block code, that n comma k block code is called as Hamming code, or also called as perfect code. Clear or not? So, if whether it is a Hamming code or a perfect code, you can identify by using single error correction. In that, you can check the equality condition is satisfied or not. Okay. Now, this is for single error correction. For two error corrections, means t equal to 2. So, 2 power n minus k, which is greater than or equal to summation I equal to 0 to t is 2 here, nci. Therefore, 2 power n minus k, which is greater than or equal to nc0 plus nc1 plus nc2. So, this is for two error corrections. Okay. For three error correction and all these things, but here important is for single error correction, because in single error correction, if this exactly equal, then this n comma k block code is called as perfect code or Hamming code. Okay, note on this. Here is one small problem which is available. Now, in a n comma k block code, the block code data length is, you have to be identified. Data length means what? N or k? N is code length, k is data length. So which means that data length is 11, which means then you have to identify this is k. Data length is 11. Determine minimum number of parity bits required. So he is asking minimum number of parity bits. Minimum number of parity bits means m. Minimum number of parity bits required for single error correction. Single error correction. So now the block code is n, I don't know, k is 11. In a n comma k block code, what is the condition for single error correction? 2 power n minus k, which is greater than or equal to n plus 1. You know that n minus k, which is equal to m, number of parity bits. Therefore, can I write like this? This is n minus k is m, which is greater than or equal to n, which is equal to k plus m. Therefore, n, which is equal to k, is 11 plus m. So, which is nothing but 11 plus m plus 1, which is nothing but 2 power m, which is greater than or equal to 12 plus m. This is the condition. But for single error correction, minimum, this is greater than, minimum means 2 power m, which is equal to 12 plus m. This condition is satisfied where m equal to 4, which is nothing but 2 power 4, which is equal to 12 plus 4, which is equal to 16. So when m equal to 4, therefore minimum 4 bits are required for single error correction. So here not only the question 4 bits are required for single error correction. Now here I want to tell you something. So what is n comma k block code? What is n? N is nothing but 11 plus m. 11 plus m is 4. Therefore 11 plus 4 15 comma 11. Therefore this is n comma k block code. Now 15 comma 11 block code. Now here, now what is n? N equal to k plus m. You know that. What is k? K you know 11. M just now you are calculating 4. Therefore what we can understand? So the total code length is 15. In that 11 plus 4 means now the total code length is 15. Now in that, now the data bit length is 11 and parity bit length is 4. Now the total information is transmitting. Now in that information bits are 11 bits are the information bits and remaining 4 bits are the parity bits. Okay. And one more thing also you can identify. Here the equality condition is satisfied or not. This is greater than. So 2 power n which is exactly equal to n plus 1. Now see here what is 2 power n? N which is equal to sorry, 2 power n minus k. 2 power n minus k. What is n minus k? N minus k which is equal to m. How much you are getting now? This is n minus k which is equal to m which is 4. So 2 power 4 which is exactly equal to n is 15 plus 1. So 2 power 4 which is equal to 16. So exactly the equality condition is satisfied. Therefore this n comma k block code which is nothing but 15 comma 11 block code. Now 15 comma 11 block code is called as perfect code. Is called as perfect code or also called as Hamming code. Is called as perfect code or also called as Hamming code. You can identify the parity bits or what is code length, what is data bit length, what is the parity bit length and which is perfect code or not. You can easily identify. And he is asking one question. Identify which of the following codes are Hamming codes. Now 15 comma 11. Yes, this is the Hamming code. This is the Hamming code or perfect code. Just now we are calculating this. This is one. And next one is 6 comma 3. He is asking 6 comma 3 block code is a perfect code or not. You have to be identified. This is n comma k, n minus k which is equal to 6 minus 3 which is equal to 3 which is m. What is the condition for Hamming code? 2 power n minus k which is exactly equal to n plus 1 equality condition. Therefore 2 power n minus k is 3 which is equal to n is 6 plus 1 2 power 3 which is equal to 7, not satisfy the equality condition. Therefore 6 comma 3 block code is not a Hamming code, not a Hamming code. Now next one is 7 comma 4 block code is a Hamming code or not. He has to ask. So n minus k which is equal to 7 minus 4 which is equal to 3. So this is a parity bits. Therefore check this is Hamming code or not by using equality condition. So 2 power n minus k, which is equal to 3, which is equal to 7 plus 1, 2 power 3, which is equal to 8 is satisfied. Therefore, 7 comma 4 block code is a Hamming code. Perfect code is a Hamming code. Now, there is a matrix representation of the block code. There is a matrix representation of a block code. Now, the code C is represented in matrix form D into G. You know C is code, D is data bits, G is nothing but, you know C and you know G is nothing but generation matrix. G is nothing but generation matrix. Okay. So G is nothing but generation matrix. Now there are two parts in the generation matrix. Now the first part is identity matrix. Now that identity matrix order is K by K. And the second part is parity. First part is identity matrix, second part is parity. This is the generation matrix. Now which is equal to data bit matrix multiplied with the generation matrix. Generation matrix first part is identity matrix. Identity matrix order is data bit length is 3 by 3. Data bit length is 4 by 4 like this. Okay. Now, so we'll take one small example such that you can understand. Now in a 6,3 block code, block code, let us take for example. Okay. Now the parity equations are P1, P2, P3 is this. In a 6,3 block code, the parity equations are D1 exclusive or D2, D2 exclusive or D3, D3 exclusive or D1. Now this is the parity equations which is given, and he is asking to determine the generation matrix. For example, I am saying, okay, let us take. So in a 6,3 block code, now represent the code and find the generation matrix. Now first we will try to find the generation matrix. This is n comma k block code, right? Therefore, now what is the generation matrix? The generation matrix first part is nothing but identity matrix. The first part is nothing but identity matrix. Identity matrix order is 3 by 3. And the second part is nothing but a parity. Now see here. Now this is the generation matrix. Now the first part is nothing but identity matrix 1 or order 3. And second part is nothing but parity matrix. Now the parity equations are P1, P2, P3. Now this is because C equal to D into G, therefore this is D1, D2, D3. Now what is P1? Now this is P1, P2, P3. So now the P1 is nothing but already given D1 and D2 exclusive are D1, D2, 1, 0, 1, 0, 1, 1, 0, 0, 0. Now P2 is D2, D3, 0 exclusive are 0, 0, 1, 1. P3 is D3, D1, 1, 0, 1. Now this is generation matrix for the given parity equations. This is the generation matrix for the given parity equations. Now if you see here, you can easily understand this is the code. Now what is the code length? The code length is 6. So the total code length is 6 bits. Now in that 6 bits, now how many are the message information bits? So the 3 are the message information bits. Now see here, this one. Now previously also I am saying C equal to the total code, which is equal to N equal to K plus M. Am I right? Not. Now this is 6, which is equal to 3 plus 6 minus 3 is 3. What is that? Now the total code length is 6. In that, now first 3 are the data bits, information bits, and next 3 are the parity bits. So the total code consisting of information bits as well as parity bits. Okay. Now this is for example. Okay. So now we'll solve. This is a way to find the code in a matrix representation of a block code, and this is a way how to calculate the generation matrix, and C is nothing but D into this G1. Now this is a C, which is nothing but, now this is D, now this is multiplied with G. Now you see here, what is this generation matrix order? 3 rows and 6 columns. Then you understand which is nothing but K cross N. Now this is K cross N, which is equal to 3 by 6. Now what is this D? Now the D is nothing but the information bits. Am I right? Not. Now how many? 3. Now this is 1 by 3. So this 3 cancel. So C matrix order is nothing but 1 by 6, which means that 1 row and how many columns? 6 columns. So this is D1, D2, D3 and parity 1, parity 2, parity 3. Satisfied or not? Now this is nothing but now code length is 6. First 3 is data bits, the next 3 is parity bits. Now this is K by N. This is 1 by K. Okay, note on this. Now see, here is one question, small question, you can easily understand. In a 6, 3 block code, Yes, this one. In a 6,3 block code, the generation matrix is this. This is one question. In a 6,3 block code, the generation matrix is given like this. The generation matrix is now in a 6,3 block code. In a 6,3 block code, the generation matrix is this. Now you know that. Now this is D1, D2, D3. This is P1, P2, P3. Now what he is asking is, now this is a 6,3 block code, generation matrix is given to you. Now he is asking to find parity equation and determine all possible codes. Now first you will try to find the parity equations. What are the parity equations? Now see here. Now this is the parity one, which is a combination of this data bits, right? Now where there is 0, you can easily identify. Now which is the combination of exclusive OR operation. Now P1 is 0 here. So if you want a 0, then you have to do the exclusive OR operation of this 0 exclusive OR 0. Am I not? So which means that, now what is P1? P1, which is nothing but D1 exclusive OR D3. And you check, this is 1 exclusive OR 0, 1, 0 exclusive OR 1, 1. So satisfied. Now come to P2. Now where there is a 0 in P2, first you identify. This is 0, means you should take a combination of these two. Is it correct or not? 0 exclusive OR 0, 0, 1 exclusive OR 0, 1, 0 exclusive OR 1, 1. So P2 is a combination of D2 and D3. And next P3. Now what is P3? P3, which is nothing but this one. This is the combination. 0 exclusive OR 0, 0, 0 exclusive OR 1, 1, 1 exclusive OR 0, 1. So P3 is nothing but D1 exclusive OR D2. This is P1, P2, P3. P1, P2, P3. Now this is the parity bits. Now determine all possible codes, right? Now determine all possible codes. Now what is the possible codes? Now data bits are how many? Tell me first now. D1, D2, D3. So if it is D1, D2, D3, now which means that 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? Now these are the possible codes. C1, C2, C3, C4, C5, C6, C7, C8. But what is the code length? Code length is 6. So in that, first three is data bits and next 3 is parity bits. P1, P2, P3. Now already parity equations are available. So P1 is a combination of 1 and 3. 0, 1, 0, 1, 1, 0, 1, 0. Now P2 is a combination of 2 and 3. 2 and 3. 0, 1, 1, 0, 0, 1, 1, 0. P3 is a combination of 1 and 2. 0, 0, 1, 1, 1, 1, 0, 0. Now this is P3. Now see here, total code length is 6. First 3 are data bits, next 3 is parity bits. Now we will find the Hamming distance. Hamming distance. Now Hamming distance is nothing but, now count the number of ones in that particular code is the number of ones in that particular code is the Hamming distance. Now there is no ones here. Now there are 3 ones. There are 3 ones. There are 4 ones. There are 3 ones. There are 4 ones. There are 4 ones. There are 3 ones. So count the number of ones in that particular code will be the Hamming distance. Okay. Now he is asking first parity equations. This is completed. Next, now all possible codes. This is completed. Now he is asking how many errors are detected and how many errors are corrected. Now easy. What is the minimum Hamming distance? Now see here. The minimum Hamming distance here is, don't take 0, okay? You should be number of ones. The minimum Hamming distance is 3. So if the minimum Hamming distance is 3, now the number of errors detection and number of error correction is available. So this is 3, which is greater than or equal to 2 plus 1. This is 3, which is greater than or equal to 2 into 1 plus 1. So here T1, which is equal to 2. Here T2, which is equal to 1, means 2 errors are detected and 1 error is corrected. 2 errors are detected and 1 error is corrected. No doubt. Now this is another question, how many errors are detected and corrected. So we can, all possibilities are available, then we can find a matrix representation of the block code. Now this is C, which is nothing but D into G. Therefore now code is nothing but now the data bit multiplied with this generation matrix. For decoding block codes, how to decode the block codes? For decoding block codes, now one technique is called as syndrome decoding. Okay, for decoding block codes, a method is called as syndrome. So we have to find first syndrome matrix. So the syndrome matrix syndrome decoding technique means first you want to find the syndrome matrix. So now let us say C is nothing but transmitted code. Let us assume R is nothing but received code. C is transmitted code, R is received code. Therefore, the syndrome decoding matrix S, which is equal to received code into H. Received code into H transpose. So this R is nothing but received code. Okay. S is nothing but syndrome matrix we have to calculate. So H we want to see. H is nothing but, this H is nothing but parity check matrix. Parity check matrix. H is parity check matrix. So if you calculate syndrome, if syndrome matrix is not equal to 0, no errors in the received code. No errors. Syndrome matrix is equal to 0, no errors in the received code. Now in such a situation, whatever the received code, it will be the transmitted code, both are same. If syndrome matrix is equal to 0, errors in the received code, we need to correct. Okay. Now this is the procedure of calculating syndrome. And what is parity check matrix? Now this is the parity check matrix. The parity check matrix and generation matrix is having some similarities. Now in generation matrix, first block is identity, but in parity check matrix, second matrix is identity matrix. First part is parity transpose, and second part is identity matrix, and identity matrix order is in minus k. Now see, this is a parity check matrix. And what is the generation matrix? The generation matrix is, first part is identity matrix and second part is parity matrix. The relation between generation matrix and parity check matrix is G into H transpose is equal to 0. Okay. Now we'll see how we can identify errors are in the received code. Okay, then we'll. Now here are the received codes, or few received codes are given to you. Now these are the received codes. So now what is given? A generation matrix is given. In a 6,3 block code, generation matrix is given. Now this is given. The generation matrix is given as this. Oh, sorry. Now in a 6,3 block code, now this is the generation matrix which is given, and he is asking to find determine parity check matrix. This is the generation matrix. Now this is first part is I, K. Now 6, 3 block code. First this is 6, 3 block code means N, K. So first part is I, K by K, which is nothing but 3 by 3. Now what is the second part? Now the second part is nothing but this is the parity, right? This is I3. This is in generation matrix. But what is asking? He is asking parity check matrix. Now H is a parity check matrix. What is a parity check matrix? In parity check matrix, H is nothing but, see here, in parity check matrix, first part is parity transports and second part is In minus K. So we can write from here, first part is parity transport, already parity is available, then that transpose you should take. Now 1, 0, 1, 1, 1, 0, 0, 1, 1, and the second part is In minus K. N minus K is 6 minus 3, 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the parity check matrix, question number 1, what he is asking. Parity check matrix, this is first part is parity transfer, second part is identity matrix. Now the second question is, now determine is there any errors in the received code. If there any errors, then you correct that error and correct that code. Okay, that is the question, and these are the received codes. For decoding of the block codes, then I just said that one method is used, that is nothing but syndrome decoding. Now what is the syndrome decoding? The syndrome decoding is nothing but S equal to the syndrome decoding S, which is equal to received code R in multiplied with parity transpose H transpose. Therefore, now this is the received code. We will check one by one received code. Now what is the H transpose? H transpose is nothing but parity check matrix transpose value is what? 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0. Now 1, 0, 1, 0, 0, 1. This is first row, second, third, fourth, fifth, sixth. Now in the received code also, the received codes D1, D2, D3, P1, P2, P3, because the total code is nothing but length is 6. In that first 3 is data bits, next 3 is parity bits. Now we will take first code. This is the first code. What is the first code? 0, 1, 0, 1, 1, 0. Now where there is a binary 1, now that particular rows you can check, you select. Now this is for example 1, 1, 2, 3, 4, 5, 6. Now in which particular position the binary 1 is there, now that particular row you select in the H transpose matrix. What are there? So second bit is 1, means second row you have to select 1, 1, 0 for calculating syndrome. Now fourth bit is 1, therefore fourth row is 1, 0, 0. Now fifth bit is 1, therefore fifth row is 0, 1, 0. Then do the exclusive OR operation, then this is nothing but calculation of syndrome. 0, 1 exclusive OR 1, 0, 1 exclusive OR 1, 0. Therefore now the syndrome is equal to 0, which means no error in the received code. No error in the received code. Therefore, whatever the received code, it will be the transmitted code. Okay. Now, what is the transmitted code and what is information in that? Now, you know, in that the first three parts are information, D1, D2, D3. This is parity bits, P1, P2, P3. So the parity is only for error detection correction. Then we are receiving code. Now the received bits are, now no error, your bits are perfectly received, D1, D2, D3, which is nothing but your information is 0, 1, 0. This is parity, we don't require that at the receiving side, okay, only for the channel. This is the way you calculate, no doubt. Second row, this is the first time I write. Second row, fourth row and fifth row. Second, fourth, fifth. These rows are the second, fourth. Now you take the second received code. Now the second received code is this 1 0 0 1 1 0. Now again, which bit positions are 1? That particular rows you select. First bit is 1, first row 1 0 1. Fourth bit is 1, fourth row 1 0 0. Fifth bit is 1, fifth row 0 1 0. Then do the exclusive OR operation of this. Now this is 1 1 0. Now this is the syndrome. So the syndrome matrix is not equal to 0. Therefore, if syndrome matrix is not equal to 0, error in the received code. If there is any error, you have to correct that particular error. Sir, then how I can know the error? So this is the received code. Here somewhere the error will be happening. So how to identify that error is, now the syndrome, you just see here syndrome. Now this is syndrome. Now this is syndrome 0 1 1 is which particular row of H transpose matrix? 0 1 1 is, where is 0 1 1? Yes, this is 0 1 1 is at here. See here, 0 1 1 is at here. Therefore, what is the meaning of that? Which means this is the third row. So third bit is an error bit. Third bit is an error bit. Rectify that error. What is the third bit? Now, as syndrome is not equal to 0. Error in the received code. So we need to correct that particular error. Now you tell me, third bit is error bit. Now in that first three are the information bits. Therefore, what is the third bit? So now the information bits are D1, D2, D3. This is the information. Parity we don't require, right? But now the third bit is error. So which means that D1 is 1, D2 is 0. Now the third bit is error. Therefore you can correct that. Now actually here it is 0. Then you can correct it as 1. This is the correction. Now this is 1 0 0. Now this is the error bit. So correct error is here. Error is here. So we can correct it 1 0. This correction is nothing like this. Now we'll see the last case, this one. concentrate, you can easily understand. This is 0, received code is 0 0 1 1 0 1. This is the received code. So now again collect. Now third row is 0 1 1, fourth row is 1 0 0, sixth row is 0 0 1. So the exclusive OR operation is 1 exclusive OR 1 0 1 and 1. So not equal to 0, error in the received code. Now this is nothing but 1 1 0 is second bit position, 1 1 0. Therefore, so this is nothing but second row. So second bit is an error bit. Now what is information? This is 0, this is 0 0 1 0 0 1. Therefore this is the second bit, error is here. So now you correct that. What is there? You correct that. So now this is 0 after correction, 0 1, and here is error, you correct that. This is the correction. Clear or not? Now what is the fourth one? The fourth one is 0 1 0 0 1 0. Now the second bit position is 1 1 1 0 and fifth bit position 0 1 0. Therefore 0 1 1 0 1. Now this is syndrome matrix not equal to 0, error in the received code, and this 1 0 0 is fourth bit. So fourth row means fourth bit, but fourth bit is a parity bit. Fourth bit is a parity bit. Means